This lesson is Chapter 3, Section 3, Polynomial and Synthetic Division. Grab your notebook and your textbook, and we'll get this one started. I'm back on the old microphone, so hopefully we have less interference and beeping noises today. So we're on page 266 in the text. When you divide polynomials, and you know a zero or a factor, you can divide the polynomial by that one factor and find another factor or polynomial that goes with it. So just like when you're dividing with regular numbers, if you divide a number by a digit, that digit times your answer gives you the number that was underneath your division box. So we're going to be taking a look at that concept today with polynomials rather than plain figures like long division with numerals. So here's an example of something that we might look at today. We have 3x squared plus 19x plus 28. We're going to divide that by x plus 4. So set up your division like always. Now take a look at the front of your factor. How many times does that x go into your first term of your dividend, 3x squared? If you multiply it by 3x, you get 3x squared. And then multiplying 3x times the plus 4 part, we get a plus 12x. Remember, the next step in long division is going to be to subtract. So I'm going to have 19x minus 12x, which is 7x. And then, of course, 3x squared minus 3x squared is gone. Drop your next term. X plus 4 then into 7x plus 28. X goes into 7x plus 7 times. I end up with 7x plus 28. Subtracting, we have nothing left. So my end answer is 3x plus 7. Now if we were to take that answer, that quotient, and multiply it again by x plus 4, and do that FOIL on there, we would come right back to that amount that's underneath our division bar. This is what's called the division algorithm. Okay, it essentially says that if you divide by a divisor and find a quotient, multiplying the quotient back to the divisor will return you to the original dividend. Okay, so I kind of drew that out for you here at the bottom. You can see the divisor on the outside, the dividend is the number inside, and of course the answer up on top is called our quotient. If we take that quotient times the divisor again, we get the dividend back. It's kind of a nice way with division where you can check your answer, is to take your answer, multiply it back up, and get that initial dividend back. And if you don't, you know you made a mistake. When dividing a polynomial, fill in any missing exponents in descending order by using 0x to the nth power for them. All right, so when you're setting up that long division, don't have a gap between, for example, x to the third power and x to the first power. You would want to fill in x to the second. Because there wasn't a term there, you have to use a coefficient of 0. So it's 0 times x to the second, which means the same thing as being gone. So let's take a look at this one. Setting this one up, notice that you don't have a regular x term in your polynomial, so that's where we need to fill in. Fill it in with a 0x term, and then go ahead and divide. So the x part of x minus 3 goes into x cubed, x squared times. Subtracting, I always kind of like to do this. If I knew I was going to subtract that bottom line, I went in through here and then I could just combine. I'm going to get x squared, or 1x squared. Then I can drop my next term. X goes into x squared, x times. And now I'm going to subtract. Subtract this one, subtract this one. Now I have positive 3x. Drop your negative 9. X goes into 3x plus 3 times. And I get 3x minus 9. Subtract. And everything cancels out, and this one turned out again even. So my quotient is x squared plus x plus 3. Again, if we were to take that and multiply it by the divisor again, we'd come back to that original dividend. Take a look with me at checkpoint problem number 3 at the bottom of page 268. We're going to divide negative x cubed plus 9x plus 6x to the fourth minus x squared minus 3 by 1 plus 3x. But notice with this problem, first of all, it is not already written in descending order. You want to change that. So when you set up your division, have your dividend in descending order. Same thing with your divisor. Rewrite that so that it is in descending order. Now we can go ahead and do our division. So 3x goes into 6x to the fourth, 2x to the third times. So then multiplying that to our 3x plus 1 divisor, I'm going to get 6x to the fourth plus 2x to the third. And we subtract. Subtract this one and subtract this one. Negative 3x cubed. Drop my next number. 3x will go into negative 3x cubed, negative x squared times. So negative 3x cubed minus x squared. Subtract. Subtract this one, subtract this one. Now they're both going to combine and give you a 0. But you have numbers left, you still have to continue to drop. 3x would go into 9x 3 times. So now I have 9x plus 3. And actually, because there wasn't a constant behind that other term, technically we would have ended up dropping both of them so that we can do this full combination. So subtract, and you get negative 6. So this particular division ended up with a remainder, and we know that oftentimes it does. So if you don't remember how to write this answer as remainder, you have your quotient first of all. The remainder has to be written in fraction form. So we had negative 6 left, and that's written over the divisor. Because technically you would be still dividing negative 6 by the 3x plus 1. Okay, so that would be our end answer. Synthetic division, I think after you see it at least, you're going to remember this from the past. It's a shortcut for that long division process. And I think most of you like it, so we'll see if you remember how it's done. Now the book didn't really go through trying to put steps for this process down, so I gave it a shot. The examples in there do demonstrate how the whole process goes. So right now make sure that you are with me on page 269. And here's my best attempt at putting all of this into words. So step 1, if the divisor is x minus k, place k on the left-hand side of your problem. Then you list the coefficients in descending term order. If a power is missing, use 0 as its coefficient. Drop the first coefficient straight down. Then you're going to take that k and multiply it by that coefficient. Place the product underneath the second coefficient. Step 5, combine. Now take the k times that amount that's underneath the third coefficient. Now you're going to keep working this process until you're all the way through the coefficient line that you had underneath your synthetic division box. So let's give it a shot. If we were going to use synthetic division on this problem, okay, our x minus k factor, remember our x minus k is that factor. So if you're seeing a positive 2 there, what was k in order to have x plus 2 as my factor? Well, k would have been a negative 2. X minus a minus 2 is positive 2, right? So put your negative 2 down off to the side. Then, give yourself the synthetic division box. Here's now where we list our coefficients in descending exponential order. We're not missing any powers of x this time. So you've got a 5, an 8, a -1, and a 6. Okay? Now, our next step said to drop the first coefficient straight down underneath. Okay, the next thing you're going to do, multiply k by 5. That's -2 times 5, and put that underneath the second coefficient. Combine. I get -2. Now I'm going to take k times that amount. So I've got a -2 times a -2, which is 4. Combine. I get 3. Now I take k times that one. -2 times +3 is -6. Combine, and I get 0. Coming out with 0 tells me that x plus 2 divides evenly into that polynomial that we started with. Now, the other thing that it tells me, it gives me what the answer, the polynomial answer was that goes with that divisor. So these coefficients, or these numbers, become the new coefficients of a new polynomial that would have combined with that initial factor, and if multiplied back together would give me that 5x cubed plus 8x squared minus x plus 6 that we started with. All right, so our answer is 5x squared minus 2x plus 3. Okay, hopefully that rang a bell. Now, the remainder and factor theorems. If you divide a polynomial by a factor and get a remainder, the polynomial evaluated with k, doing f of k, would end up equaling that remainder. Okay, so this is kind of a cool little deal. We're going to take a look at a couple of things that involve this. First, I'm going to take a look at problem number 47 with you guys from the homework, because I'm assigning to you problem number 48. So if you look at problem number 47, the directions say to write the function in the form f of x equals a factor times the quotient plus the remainder. Okay, so x minus k, remember, is that factor. Q of x is your quotient. All right, so your answer, plus a remainder. All right, so let's take a look at this one. First of all, in our problem, they give us that k equals 4. So that would have come from a factor of x minus 4. Okay, so keep that in mind. If we're going to use synthetic division, they're flat out handing you k, so go ahead and put that 4 out here. Now we know we need our coefficients next. 1, -1, -14, and 11. Let's go ahead and do our synthetic division. Drop the first coefficient. 4 times 1, 4. Combine. 4 times 3, 12. Combine. 4 times -2 is -8. Combine, and we get 3. 3 is our remainder. Okay? So how can I write then the function of that form that they asked for, that f of x is equal to x minus k times quotient? Well, let's make our numbers here from our synthetic division back into a polynomial. If I've got 3 terms here, I've got a 1x squared, I have a 3x, and I have a minus 2. All right, so that's my quotient. That was my answer for my division. So fill in all those things in that order that they asked us for up there. The x minus k was x minus 4. Our quotient function, our answer was x squared plus 3x minus 2 plus our remainder, 3. So there's that answer that they're asking you for. Okay? Then it says demonstrate that f of k actually equals r. All right, so let's plug in k equals 4 to our function. So 4 cubed is 64, minus 4 squared. 14 times 4 is 56. And sure enough, if you put that all together, it does end up equaling 3, which it was, in fact, what our remainder back here was. Okay, so that's just a little bit of a demonstration proving that remainder factor theorem. let's use that remainder theorem again to find some more function values. If we're going to do f of negative 1, okay, let's go ahead and divide by that k value. Do synthetic division with that k value. So they're telling us k is negative 1. Use it. My other coefficients, we had 4, 10, negative 3, negative 8. So go through the process. And we get 1. So this is telling us that if we plug in negative 1, we get out a positive 1 remainder. So 1 point that would be given, or 1 value that we get out, is 1. So a point that works for our function and would thus end up on our graph if we were to graph this thing is the point negative 1, 1. All right, I picked C as well on this checkpoint number 5 to do because it gave us f of a half. Well, that doesn't matter. You can still use a half as a k value. We still have the same coefficients, same problem. Still drop the first number. Now 1/2 times 4 is 2. Combine, we get 12. 1/2 times 12 is 6. Combine, you get 3. 1/2 times 3 is 3/2. And if you take negative 8, which is technically negative 16/2, right? And combine them, you get negative 13/2. So when we put in a half, we get out negative 13/2. So let's just prove that that actually works. Sorry, I'm back to not being able to reach that side of my board, so I can't talk you through any of that, but I think you saw what I was doing. Now, 4 times 1/3 cubed will be 4 times 1/8. 1/2 squared is 1/4. And then negative 3 times a half is negative 3/2, and then we still have the negative 8 at the end. 4 times 1/8 is 1/2. 10 times 1/4 is 5/2. And then since everything is in halves, I'm going to go ahead and rewrite the negative 8 as 16/2. And if you combine all of that together, you do in fact get negative 13/2. So another point that would end up on this graph is that one. Now the next problem, forget which checkpoint problem this was, looks like number 6. Show that x plus 3 is a factor of the function given here, and then find the remaining factors of f of x. All right, so if it's telling us or suggesting that x plus 3 is a factor, let's go ahead and use synthetic division to find out what we're left with when we divide that out. Okay, if we've got x plus 3 as a factor, my k is negative 3. My coefficients, I have a 1. Notice you have a missing x squared term, so you need to use a 0, and then negative 19 and negative 30. So start your process. Drop your 1, multiply k times that, combine. Multiply k times negative 3, positive 9, combine. And then multiply negative 3 by negative 10, and we get positive 30. So it does come out even. That was in fact a factor. What polynomial does that leave you with here with these numbers 1 and negative 3 and negative 10? Well, with 3 digits there, I know the first one is going to be a 1x squared. Then I'll have a negative 3x. and then a negative 10. Now that polynomial, we can factor that more. Okay, so the second part of this problem was find the remaining factors of f of x. So if that's our polynomial that we get after taking the first factor out, let's find the other factors that make this thing up. Now you could again carry out synthetic division if you knew one of them, but you don't. So we're right back to old school finding factors. So negative 5 and positive 2 will factor that polynomial. That's not a very bad one. So not only was x plus 3 a factor, but x minus 5 is a factor, and x plus 2 would be a factor. All right, now your assignment, find it on page 272. Do lots of them. Okay, have fun with this assignment because you have some true blue algebra for once. I do want 4 of these problems handed in on Monday. I think you should be able to go through them. Remember that when you get to number 48, I purposefully did 47 in the video so that you'd have one to guide you through those directions. And we'll see you guys on Monday.